Hi, we'll start in few minutes. Matja is online. Hi, Matja, can you hear me? You must turn on your sound.
Yeah, I can hear, yeah.
Okay.
But I cannot share my screen.
Uh, I will promote you a little bit. Make presenter. Now you are the presenter.
Okay. Do you see now my screen?
Yeah, it's coming. Yeah, it's there. It is. You can put it on full screen. I see everything, the border of your window.
But I put it on the screen.
That's not. Uh, it's still showing the borders of your presentation.
Uh, so on my screen it is on the full screen. So
But perhaps you are sharing the wrong window.
let me try again. Is it now better? Is it okay now?
It still looks the same.
You are showing just part of your presentation and a lot of stuff of your. Try to
What
press
else do you see?
Control L.
Yeah, I put Control L. But what else do you see?
Perhaps I see your Acrobat window, not your presentation. I think you need to choose to share your entire window, your
Okay,
entire
no,
monitor.
okay, so now I'm sharing the whole
The
window.
whole window.
Is it now better?
I think it's better. Just a moment, I will connect here with the TV. 1 second. Hello? Matja, you can go.
Can you hear me?
Yes,
So can I start now?
you can go.
Okay, so hi everyone. It's I'd like to thank organizers for giving me opportunity to talk about my work. So I'll talk about ranks of elliptic curves and the deep neural networks. So what we'll talk now is joint work with in two distinct projects with Domagoj Vlah and Zvonimir Bujanovic. They're both from the University of Zagreb. So this is the outline of the talk. So first I'll start with the introduction to the elliptic curves and to the ranks of elliptic curves. So this is for those who are not familiar with these topics. After that, I'll talk about the first project about computing a rank using deep neural networks. So this is a joint work with Domagoj Vlah. And in the second part of the talk, I'll talk about the recent project with Zvonimir Bujanovic. So this is the work in progress. So I'll talk about Mesner-Nagel sums, in particular about murmurations of Mesner-Nagel sums. Okay, so to start with the introduction to elliptic curves, I'll go back to the 3rd century to the Derfantus from Alexandria. So in his famous books Arithmetica, he mentioned one problem, which in the modern language we could express as to solve the equation y times 6 minus y is equal x cubed minus x. So he wanted to find the solution that is in positive rational numbers. So he also provided the solution to this equation, and of course his solution was not written in the form that I'm going to present it, but what he essentially did is that he can sketch the curve representing this equation, and then he noticed one obvious rational point, and this is the point minus 1, 0. And then he just took the intersection of the tangent line through that point and the curve. And there's one more point that this line intersects, and then one can compute that this point has coordinates 17/9 and 26/27. So in this way, he obtained the solution that he wanted to find, a non-trivial solution from this trivial one. So today we know that this tangent and chord process, this method, so if you use this method starting from these obvious points minus 1, 0, and 0, 0, you can obtain all the rational points on this curve. And so in general, we can define the curve of the previous form in the following way. So this is called the elliptic curve, and these coefficients, in our case, A1 till A6, are going to be the rational numbers. So what we're going to be interested in is the set of rational points on this curve, so the set of rational solutions, and one can show that this set is the group with respect to the operation previously mentioned. So you take 2 points and then you draw the line through 2 of them, and this defines you the 3rd point. So here the point at infinity is the natural element. And one more thing, that we'll need from this theory of elliptic curves is an invariant that's called conductor. So throughout this talk, we'll denote this invariant by n. So we don't need to define it precisely, but you can think of it as a number that tells you something about the complexity of this curve. So the larger the number, it's harder to find solutions to this equation. So what I was referring earlier is this Mordel's theorem, which tells us that this set of rational points with respect to previously defined operation is a finitely generated abelian group. And the structure theorem for finitely generated abelian groups tells us that it can be represented as the sum of finite of the group of the finite element of the group of the elements of the finite order and the free part. And the number of the copies of z in this free part is called the rank of elliptic curves. And this is the main focus of what we are going to talk today. So in the previous example, the rank of that curve was 2. So now I'll say something about computing the rank of elliptic curves. So in general, the rank is quite a mysterious quantity, so not much can be said about it. So it's not even known is the rank unbounded. The current record is 28. So to illustrate this point, I will show you an example. So this is the LKS rank 28 curve. And these are the 28 generators of the set of rational points on this curve. So as you can imagine, it's not easy to find such examples, and there's not really any good method which will tell you how to find these curves or how to find the rank of elliptic curve. So the reason for that is that in order to compute the rank of elliptic curve, you really need to have some method of finding rational points on an elliptic curve, and that's a difficult problem. If you use the usual descent algorithms, usually this will eventually reduce to the naive point search on some auxiliary curves, and there's no known algorithm which will compute the rank in all the cases. So this is a difficult problem, and so the question is it somehow possible to determine rank without finding explicit generators, so without finding the solutions? And the answer is yes, so I'll talk a little bit about that. So I have to mention now the famous Burcham-Swinner-Dyer conjecture. So first, for every prime p, we will define the set of numbers AP, which is essentially a number of points on elliptic curve over the field FP. So we will be using these numbers throughout this talk. And we can define a Hasse-Weil L function using this number. So we can define it as the convergent infinite product, where this S is the complex number with the real part greater than 3/2. And the famous modularity theorem tells us that this L function then extends to entire function on the whole complex plane. And BSD conjecture, or Burcham-Swinner-Dyer conjecture, conjectures that the order of vanishing of this L function, of this extended L function, at S equals 1 is equal to the rank of elliptic curve. So idea is to use this conjecture to conclude something about the rank of elliptic curve. Okay, so this is not going to be precise algorithms. These are going to be the heuristics, and we call these heuristics Mestre-Nagel sums. So their main role is not to tell you precisely what is the rank of elliptic curves, but let's say if you're interested in finding elliptic curves of high rank, then it will give you the candidates for the curves of the high rank. So these heuristics can be quickly computed, and if you have a large number of elliptic curves, that you want to check their rank. So you can just run these heuristics on these curves, and then these heuristics will tell you which curves are the probable candidates for the curves of high rank. So for example, this is one of these sums. So how to connect this sum to the L function? So as it's written here, exponential of the minus of this sum is the partial product of the L function evaluated at s equals 1. So here we are just looking at the partial product. In general, this does not converge, but we're just looking at the product of primes less than b. And then one expects this quantity to be larger if E has a large rank, since then this partial product should rapidly approach 0. Okay, so, and this sum, for example, was used by Elkies and Klagsburn as a first step in finding the rank record-breaking curves with fixed cyclic torsion. Okay, so now I'll talk about our approach. So idea is to use deep learning algorithms for the rank classification, and these methods or these models are based on convolutional neural networks. So these networks take as an input conductor of elliptic curve and the sequence of normalized APs. So this is the input. And so we are looking at these APs in the certain fixed rank. So in our experiments, we had 3 bounds, so 1,000, 10,000, and 100,000. And they output the rank of elliptic curve. So in a way, it is in a way similar to the Mestre-Nagel sums, because they also take as an input this set of normalized, or this set of APs in certain range. So this project was inspired by the paper of He, Lee, Oliver, machine learning invariants of arithmetic curves, where the authors successfully used logistic regression to classify elliptic curves of rank 0 and 1. So in order to evaluate the performance of our algorithm, we decided to compare it to the performance of the Mestre-Nagel sums. So we were considering 7 different Mestre-Nagel sums, and we also considered one neural network which took input all these seven sums. So we call this network omega. So the reason why we were using neural networks to model this Mestre-Nagel sum is that it's not a priori clear how we're going to decide on that one number what is going to be the rank of elliptic curve. So we decided to train neural network to do that task for us. And also, since this cutoff, this answer, critically depends on the conductor of elliptic curves, we also decided to provide input to this network's conductor of elliptic curves, as well as the Mestre-Nagel sum. And as a side product of this, the training of these networks revealed the optimal cutoff of the specific Nagel sums for the rank classification. Okay, so just to give you some impression, so these are the 3, 3 out of these 7 Mestre-Nagel sums that we consider. So this first sum is going to be important in the second part of our talk as well. And as I mentioned earlier, omega is a neural network that takes as an input conductor of elliptic curve, and also input, we take here input all 7 previous Nagel sums, and this neural network worked much better than all other Mestre-Nagel sums individually. Okay, so now say something about the training process. So we trained our models on two data sets. First was the LMFDB. So this is the well-known data set which consists of 2.9 million isogeny classes of elliptic curves. But it's also important to mention that it really contains three different data sets. It contains all curves of conductor less than 500,000, all curves whose conductor is 7 smooth, and all curves of prime conductor less than 300 millions. And the curves in this data set have rank between 0 and 5. But since we also wanted to check our algorithm on the curves of higher conductor and the higher rank, we made our own data set, which contains around 2 million elliptic curves over Q, and all these curves are with trivial torsion and conductor up to 10 to the 30. So these curves have rank between 0 and 10. So let me say a few words about the construction of this custom data set. So for the curves of rank 0 and 1, we just randomly generated some Bayesian coefficients. And for the curves of the higher order, we obtained them as a random specialization of the pencils of cubics through randomly selected rational points in the plane. So basically, we just select some points with the small height, and then we just look at the qubits that go through those points, and we sample some other points from those families, and this way we get our data set. After we sampled our curves, we computed, or we tried to compute the rank with the PARI-GP L-rank method, and so here we were also using the parity conjecture, and we also discarded curves for which we could not find rank for certain. Okay, so there are some problems with this custom-made dataset. So it's not, it's in bias in a certain way, and the thing is, if you listen to this construction, you'll see that it's constructed in such way that it will have this rational points of the small height. So consequently, it means that that many elliptic curves in this family will have a small regulator. And this is not something that you would typically expect, because you typically expect the regulator to be large if you have a large conductor. So in a certain sense, there is a bias in construction of these elliptic curves. And also this bias is relevant for what we are doing, because if you, for example, look at the previous Messer-Nagel sum, you can see that it follows from the original Bircham-Sventodary conjecture that you expect this sum to behave as log of some constant a plus rank times log on b. And essentially this constant a conjecture also depends on the regulator. And this is the problem, because what the Messer-Nagel sums algorithms ultimately do is that they express this term, which also depends on this constant. So there's this bias in this data. But since our only aim is to compare CNN algorithm with the Messer-Nagel sums, maybe it's not so important that this database elliptic curves are not representable, that they are biased. Okay, so let me explain our experiments. So for each neural network, so in total we had 9 of them, we performed 24 tests by varying first the data set, then the range of APs that we considered. So we considered 3 ranges: 1,000, 10,000, and 100,000, and also by arranging the choice of the test curves. So we have two modes. So we either uniformly selected 20% of the curves from the data set uniformly, or we choose the curves of the top conductor range. And in that case, of course, we didn't train our curves, our algorithms on that range. So in this mode, we also got information how well our neural network generalizes data to the data generalizes to the data that it didn't see. And also we look at the two types of classification, the binary and all the ranks classification. So in the binary classification, we were only interested in deciding whether the curve has a small rank or not. So small rank for the LMFDB means the rank from 0 to 3, and in the custom data set, it's the ranks from 0 to 6. Or, okay, so it's high rank is 8, 9, and 10, and for LMDB, high rank means 4. So we did not consider the curves of rank 5 because there are very few of them. Okay, so I'll not say much about the architecture of elliptic curve of this deep neural network. So I'll just say that the network is really deep. So in the smallest case, so b is equal 1,000. So it has around 773,000 parameters. And one more thing, so I need to say how we measure the quality of the classification. So for that we use the Matja correlation coefficient. So this is the well-known measure of the quality, and it is especially good since it takes account the fact that we have here classes of very different sizes, because there's much less elliptic curves of high rank than those of the smaller rank. So if you don't take that into account, it may happen that your algorithm will neglect some class altogether. But this correlation coefficient is doing this job well. So here is how it works in the case of the binary classification. So it's given by the following formula, which takes into account also the number of true positives, true negatives, false positives, and false negatives. So it gives a number in the segment from -1 to 1, and the value of 1 tells us that we have the perfect classification. Okay, so now I'll talk a little bit about results. So first, kind of side result that we got from the training of Messer-Nagel sums is this following graph of the cutoffs for the S. So this is, for example, this S5 Messer-Nagel sum. So here, this graph tells us how to choose the cutoff for each of the ranks as the function of the conductor. So we see that how each of these cutoff range is changing as the conductor is increasing. Okay, so now we'll compare these different models. First on the LMFDB dataset. So here we are looking at the results in the uniform test mode. So this is the mode where we choose 20% of all the curves in the dataset as a test curves. So here we see that the convolutional neural network performs much better than the Mestre-Nagel sums, and we also see that the omega neural network, the one that takes into account all Mestre-Nagel sums, also performs much better than this Mestre-Nagel sums. To give you some idea what these numbers mean, so if you look at here, a confusion matrix for the CNN in case when P is less than 100,000. So here we see that this classification is almost perfect. So also the omega neural network also works very well. There is some problems with classifying curves of rank 0 and 1, and everything else really works perfectly well. If you look at the top conductor range here, the results are much more are not that good. The reason is that, as I mentioned earlier, the higher the conductor is, it's harder to classify. So you need more APs to determine the behavior of that L function. But here we still see that convolutional neural network performs much better than all other algorithms, especially in the case when P is less than 100,000, we'll have almost a perfect or very good classification quality. Okay, so this is maybe the most striking contrast. So if we look at the confusion matrix of CNN and S0, in case when P is less than 10,000 in this top conductor range, we see that we see the huge difference. So if you look at the confusion table of S0, you see that it really has lots of problems with curves of the small rank, while CNN works very well. So to summarize the performance on LMFDB dataset, we can say that for all rank classification in uniform test case, for P less than 10,000, CNN with MCC of 0.9958 misclassified only 0.25 curves, while the best Messer-Nagel sum in the same mode, which is S2, misclassified 8.1% of the curves. In all rank classification of top conductor rank, MCC of CNN was 0.928, while the Matja correlation coefficient of the best Messer-Nagel sum is only 0.5, which is kind of the huge difference. Okay, so now we'll take a look at the custom dataset. So here expectedly, since here we have curves up to conductor 10 to 30, the results are much worse. In this uniform test mode, we see that the CNN is still performing better than the other models, but here the differences are not that great. So also here, if you take a top conductor range, so if you look at just the classification of the elliptic curves of the conductor between 10 to the 29 and 10 to the 30, we see that all the models are not performing very well, and here we see that the CNN is not any better than the other sums. So here the omega is out of performing the CNN. So to highlight this performance on the custom dataset, we can say that the classification here is much more challenging. So in all rank classification with P less than 10,000 and uniform range, Matja correlation coefficient of CNN is 0.728, which means that it misclassified 23% of the curves, but still only 3% of the curves prediction is worse than the error is more than 1. In the same mode, the best Messer-Nagel sum is classified 26% of the curves. So in the top conductor range, MCC of CNN is 0.3 019, and in this case it misclassified 61% of the curves, while for 12% of the curves prediction missed true rank for more than one. And the best Mestre-Nagel sum in this mode, S2, has MCC of 0.3291. Okay, so now we can ask ourselves what kind of information can we get from this data. So one question is to try to determine how does conductor and the range that we have chosen B influence the quality of classification. And to try to characteristically answer this question, we can look at the toy model for detecting rank 0 curves. So for that, we can numerically evaluate the L function at point 1 using the approximate functional equation, and we'll get the formula of the following form. And now we can see from that square root of n appearing in exponential function that to have any chance of getting information about the rank from this formula, we somehow have to choose this b to be around, at least around the square root of n at minimum. So it kind of makes sense then to investigate dependence of the quality of the classification of our various models as measured by the Matja correlation coefficients, depending on the quantity of b over square root of n. So, for example, this figure shows this relation. So this is the graph as a function of the logarithm of the b over square root of n for case when b is equal to 10 to the 5th. And so on the y-axis we have the MCC of those models. And so here we have chosen CNN, omega, and S1. And here you can see that the quality of the classification for CNN is better than those two in each interval. So okay, so this is all that I want to say about this first project. So now I'll talk more about the study of the Mestre-Nagel sums. So I'll talk about the murmurations of the Mestre-Nagel sums. So I'll focus here on S0. So S0 is given by the following formula, and it is known by the work of Kim and Murty that if this limit as b goes to infinity exists, then this limit is going to be the minus analytic rank plus 1/2. Idea is to use this formula to try to guess the rank of elliptic curve. So the problem is the same as before. So we are given the conductor and this number, and we need to determine the rank. And the natural question that comes to one's mind, especially one wants to maybe use this method in some application, is what is the impact of the size of the b on the quality of classification? And the question is it always advisable to choose b as large as possible? So intuitively one will say yes, because you just want to have as most APs as possible. So by choosing b as large as possible, you would certainly obtain that. But what we will see, the answer here is no. And in the rest of this talk, I'll try to explain why is this the case. Okay, so if you want to make experiment about this question, so we are going to focus on the classifying curves of rank 0 and 1, and all our research on the Mestre-Nagel sums, we are using the Stein-Watkins and Balakrishna database of elliptic curves. Here it's kind of straightforward what one needs to do if you want to answer this question using a Messer-Nagel sum. For given conductor range, you must determine the optimal cutoff. So that will be the number that will separate in optimal way curves of rank 0 from those of rank 1. So it's natural to examine the averages of these Messer-Nagel sums within the families of curves of rank 0 and rank 1 separately, of course with a specific conductor range. So this is how the picture looks in one particular conductor range of elliptic curves of conductor between 40,000 and 45,000. So in this range we have around 1,000 curves, and on this graph we can see the blue line is the average of the curves of rank 0, and the orange line is the average of the curves of rank 1, and this blue interval is 90% confidence interval for these curves of rank 0, and the orange interval here is the 90% confidence interval for the curves of rank 1. And what one sees here is that we can observe this local maxima in this graph, which really tells us that the best chance to have a good classification based on this data is to choose a B that corresponds to one of those, or precisely to this first local maximum. So it's better to choose this B than maybe some other larger B in this interval over here. Okay, and so we want to understand this better. So first questions here that we ask ourselves is, can we predict the location of this local maximum? And surprisingly, we can. So our data indicates that this first local maximum occurs approximately at for B equals 0.08 times conductor, the second at 0.65 times n, and the third at 1.7 times n, where n represents the start of this conductor range. So later, if I have time, I'll show you the video that illustrates this finding, but now we just try to explain this phenomenon. So the question is there any explanation for this phenomenon? Okay, and now I will mention a recent result of He, Lee, Oliver, and Pozniakov. So they uncovered a remarkable oscillation pattern in the averages of these APs of elliptic curves with a fixed rank. So in their paper, this was the rank 0 and 1, and conductor within a specified range. So maybe to explain this idea or these findings, I'll show you this graph from their paper. So on the x-axis, you have primes till 1000, and blue dots represent the averages of AP if you only look at the curves of rank 0, while the red dots represents the averages of AP in this family of elliptic curves in this specified conductor range, but with rank 1. And what I have noticed is that very interesting oscillatory pattern in these averages. Sutherland further observed similar phenomena in more general families of L functions. So, for example, for Cas forms with fixed root number. And also, very recently, Zubrilina explained this phenomena for the families of modular forms and their root numbers. So very roughly, she obtained that the main term of the average of AP of modular form times the root number of the modular form for fixed prime P and for forms of conductor around X is a function of P over X, and this was previously observed by Sutherland. And she computed that the main term of the average is equal to some very explicit function. So here these CIs are some explicit positive constants, and CR is also some explicit positive function. Okay, so we tried to explain our data using her result. So we can use this formula as a heuristics, and here we disregarded all the error terms to approximate the averages of our S0 Mason-Lagrange sums over the families of rank 0 and 1. So this works because if you recall the formula for the S0, in this formula, you have some kind of linear combination of these APs. So if you look at the average of these sums in some family, the average of these APs will come up naturally. So, to demonstrate this, so we fixed a conductor range at 100,000 and we plot this average as a function of x. So we plot this S of xn for x ranging from 0.1 till 2. So we're hoping to observe local maxima at points of 0.08, 0.065, and 1.7. So what we got is the following graph, and I don't know is it surprising or not, but we really observe these two maximums. So the first local maximum is at 0.65, something a little bit greater than that number, and here it was the first one is at 0.08 and the second one is around 0.65. So I would say it was surprising for me that this graph really explains that phenomena. While for this third maximum, it was 1.7, so it is not discernible in this graph. Okay, so now this is some kind of heuristic explanation of this phenomenon, and of course now we would like to prove something along these lines. Okay, so to wrap this talk up, so a few concluding remarks and the future work. So it is unclear why the convolutional neural network works much better than all of the other Mestre-Nagel sums models based on the curves from the LMFDB. So the interesting question is, did CNN discover some new mathematics? And this is something that we would like to investigate, or that we are investigating right now. The second question is, and this is also something that we are working on now, is to construct new and improved Mestre-Nagel sums. So for example, we can try to construct sums that use maybe two different B's or more different B's. So the question is, are these sums going to perform better than the Mestre-Nagel sum with only one B? And of course, the third question is, can the heuristics governing the murmurations of S0B be rigorously proven? Okay, so thank you for your attention, and for more details, you can look at the following paper.
Hi, Matja.
Oh, hi. Hi. So, can you hear me?
You see the Steven's question in the chat box?
Yes. Yes. I mean, did you hear my lecture?
Yes, we hear you.
Okay. Okay. So yeah. So yeah. It's hard for me to say something about the curves that were mischaracterized. So yeah. So as I mentioned this in my talk, if you use the Mester-Nagel sums to do this classification, then it may happen that if the regulator of the curve is large, or maybe the size of the pitch of average group, that might affect the leading term, or at least this thing that Mester-Nagel sum is trying to compute. So So what we tried in this second part of this research so what we did, we constructed a network that takes on the input two values for two different B's. So in that case, our hope was that the network will, from the two values, figure out that, let's say, the coefficient is big, and then let's say what you can do maybe is subtract these two numbers, and then you'll get something that depends only on the rank. Indeed, such network performed better than the original network, but not much better. So in a way, I think that this was not very significant in this classification, this constant term.
Thank you, Matja. Maybe we can discuss about this question more on the free discussion time.
Sure, yeah.
Okay. Thank you again for giving talk. Anyone has more questions? Okay. Thank you, everyone. We can come back in 2 hours.